Voyager turned its camera back towards Earth, capturing what is essentially Earth's first ever selfie. This picture, known for its pale blue dot, marked a monumental moment in our understanding of our place in the universe. For 4 decades, Voyager 1 has journeyed through space, bringing us unprecedented information. Each discovery seemed impossible until scientists reviewed and confirmed the data. Recently, Neil deGrasse Tyson confirmed that Voyager 1 detected 500 objects passing by in space, a discovery that could change everything we know about space exploration. Voyager 1, launched in 1977, has been cruising through space for almost half a century. Despite its age, the spacecraft is in remarkable condition and usually operates smoothly. However, it was recently caught off guard, leading to strange behavior. To put this in perspective, Voyager 1 is over 14.5 billion miles away from Earth, traveling at about 3.6 times the distance between Earth and the Sun per year. This is impressive for a spacecraft that has been out there for so long. The mysterious objects Voyager 1 detected are fascinating as it somehow spotted 500 unknown objects passing by in space. These are things we haven't seen or identified before, providing totally new information that no one expected. One possibility is that the spacecraft's age is catching up with it. Voyager 1 was launched in 1977, so its circuitry is around 45 years old. It would make sense if the computers didn't work the same way, but this hasn't been the case so far. The spacecraft's long life is due to its dual redundant computer systems. Each Voyager spacecraft featured 2 sets of command computer subsystems, flight data subsystems, FDS, and altitude and articulation control subsystems. This redundancy allowed for seamless transitions between systems and the ability to activate dormant computer components, preserving their lifespan. Power management is crucial for maximizing efficiency. Voyager's instruments rely on hardwired logic due to power budget limitations and time constraints during development. Electrical engineers simplified systems using hardwired logic. The computer systems aboard Voyager 1 and its twin, Voyager 2, had 6 onboard computers organized as a distributed system with 3 dual redundant pairs. Ongoing power management is critical for maintaining Voyager 1's operational integrity. Engineers devised measures to conserve and optimize power usage, including selectively powering down non-essential systems. For instance, heaters associated with certain science instruments were switched off. These heaters maintained instruments at specific temperatures for optimal functioning. By deactivating them, power consumption was significantly reduced, extending the spacecraft's lifespan. This decision involves careful evaluation of the trade-offs between power conservation and scientific objectives. Engineers collaborate with scientists to determine the impact of deactivating specific systems on the quality and availability of scientific data, aiming to strike a balance that maximizes power efficiency while maintaining necessary functionality. As Voyager 1 travels farther from the Sun, available solar energy decreases. The spacecraft adjusts its power usage accordingly, ensuring efficient allocation of power resources to support critical operations and data transmission. Ongoing technical advancements and improvements in power management techniques have allowed engineers to refine and optimize Voyager's power systems. Enhancements include more efficient power distribution, improved battery charging methods, and advancements in power regulation and control. By implementing meticulous power management strategies, engineers have extended Voyager 1's operational lifespan, enabling it to continue its remarkable scientific journey through the depths of space. Careful allocation and conservation of power resources ensure critical systems remain functional, allowing the spacecraft to transmit valuable data and insights back to Earth for as long as possible. Considering Voyager was only supposed to last for 5 years, still sending back information almost 50 years later is astonishing. This longevity is due to the meticulous work scientists have put into ensuring the spacecraft remains functional. Despite the extensive work and skill involved, unexpected events can still occur in deep space. Generally, one might expect the spacecraft to interact with meteoroids, asteroids, and space rocks. However, Voyager sending messages about detecting 500 objects was unexpected, causing significant concern. Researchers called this an anomaly because the signals came unexpectedly, and there was no clear way of figuring out what was happening. Voyager 1 started transmitting mysterious telemetry data back to Earth. Despite unusual readings, the spacecraft remained responsive to commands from mission control, though there was a slight communication delay. Voyager 1's antenna continued to point toward Earth, ensuring the spacecraft could receive and execute instructions effectively. Scientists were confused by the mysterious data, but Voyager 1 appeared to be functioning correctly, continuing to gather and transmit data. The anomaly did not trigger any onboard fault protection systems, which are designed to activate when anomalies are detected, putting the spacecraft into safe mode for investigation. After careful investigation, the anomaly was traced back to the Altitude and Articulation Control Subsystem, ACS. The ACS is responsible for orienting the spacecraft and controlling its movements. It was discovered that the ACS had been sending telemetry data through an onboard computer that had ceased functioning years ago. This outdated computer, which should not have been involved in data processing, had somehow become entangled in the telemetry transmission process, leading to corrupted information being sent back to Earth. To fix the anomaly, the mission team instructed the ACS to redirect telemetry data to the appropriate functioning computer. This fix was considered low risk and was successfully executed. However, a major challenge during this investigation was the significant time delay in communication due to the vast distance separating the spacecraft from Earth. Voyager 1, approximately 14.6 billion miles away, requires a considerable amount of time for radio signals to travel. The mission team at NASA's Deep Space Network sends commands to Voyager 1, which travel as a radio signal at the speed of light. The Deep Space Network, DSN, is an extensive network of enormous radio antennas strategically positioned across the globe, enabling NASA to establish communication links with spacecraft exploring the far reaches of our solar system and beyond. The DSN collaborates with various space agencies, including the Soviet, Chinese, Indian, and Japanese deep space networks, along with the European Space Agency's ESTR. The DSN comprises 3 deep space communication facilities situated approximately 120 degrees apart: Goldstone in California's Mojave Desert, Madrid in Spain, and Canberra in Australia. This strategic placement ensures continuous coverage and observation of spacecraft as the Earth rotates, making the DSN the largest and most advanced scientific telecommunication system worldwide. The DSN operates on the principles of radio wave transmission, communicating with spacecraft by utilizing colossal antennas at its stations. When transmitting data from the spacecraft to Earth, DSN channel 18 is typically used, utilizing frequencies of either 2.3 GHz or 8.4 GHz. When sending signals from Earth to Voyager 1, a frequency of 2.1 GHz is used. Even at the tremendous speed of light, the signal requires approximately 22 hours to reach the spacecraft. This time delay poses unique challenges, requiring careful planning and precise execution of commands during anomaly investigations. The time delay prolongs the diagnostic and troubleshooting processes. Commands must be carefully crafted considering the anticipated response time. This time delay also limits real-time control and interaction with Voyager 1. Unlike missions within our solar system, where the delay is relatively small, interstellar distances introduce a significant lag, making instantaneous conversations or quick adjustments impractical. After extensive back and forth, the anomaly was fixed at the source, and the faulty computer was shut down. However, the reason why the ACS started routing telemetry data to the incorrect computer remains a mystery. It's suspected that the ACS received a faulty command from another onboard computer, but the exact cause has not been found. Possible explanations include cosmic radiation, extreme temperatures, and micrometeoroid impacts. Cosmic radiation, consisting of high-energy particles from distant stars and other celestial sources, fills the space between galaxies. These particles can penetrate spacecraft structures and interfere with electronic components. Intense radiation can cause electrical disruptions, alter data signals, and lead to memory errors or data corruption. Extreme temperatures also pose a significant challenge. Voyager 1, in the outer region of the solar system, faces extreme cold, impacting electronic components' performance. Micrometeoroids, tiny dust particles or fragments of comets and asteroids, travel at high speeds and can cause damage upon impact. Even a minuscule collision with a sensitive electronic component can disrupt functionality or create interference in data transmission. Another popular explanation in the science community is the possibility of a highly advanced alien civilization with capabilities far surpassing our own. Considering Voyager 1's distance from Earth, it's possible it encountered an alien civilization. Aliens could have manually turned on the old computer and sent the message. If Voyager 1 did make contact with aliens, it has the instruments needed to gather detailed information. The spacecraft carries a remarkable array of scientific instruments, part of the Attitude and Articulation Control subsystem, ensuring stability and communication with Earth. Among Voyager 1's instruments is the Cosmic Ray subsystem, measuring the intensity and properties of cosmic rays. The magnetometer analyzes magnetic fields encountered in space. The photopolarimeter subsystem captures and analyzes light, providing insights into interstellar dust particles and celestial objects. The Plasma Science instrument studies the properties of plasma, providing data on densities, temperatures, and velocities. The Low-Energy Charge Particle instrument examines the composition and energy distribution of low-energy charged particles. The Plasma Wave subsystem detects and analyzes naturally occurring radio and plasma waves, studying the interstellar medium's properties. The Ultraviolet Spectrometer measures ultraviolet light intensity from celestial objects, studying the interstellar medium's composition and physical properties. The Infrared Radiometer analyzes the thermal emissions of objects encountered on the cosmic journey, revealing their temperatures and thermal properties. The Interferometer examines infrared light interference patterns, studying gases and particles' composition and physical properties. The spectrometer, operating alongside the infrared radiometer, measures light absorption and emission, providing clues about the interstellar medium's chemical makeup. Voyager 1's high-gain antenna ensures findings are transmitted back to Earth, maintaining communication with mission control. Voyager 1 and Voyager 2 provided the first direct evidence of the heliopause in 1993, a critical milestone in our understanding of the interstellar medium. The heliopause marks the boundary between the solar wind and the interstellar medium, where the solar wind's pressure balances the interstellar medium's pressure. Both Voyager spacecraft detected a substantial decrease in solar wind speed and an increase in interstellar medium pressure, confirming the heliopause's existence. Voyager 1 reached the heliopause in August 2012, making it the first human-made object to enter interstellar space. This achievement opened a new chapter in our exploration of the cosmos and provided invaluable data on the transition between our solar system and the vast expanse beyond. In a world where assumptions and expectations often dominate, the work of scientists reminds us to embrace curiosity and a sense of wonder. Voyager 1's detection of 500 objects passing by in space showcases the universe's infinite possibilities and our ongoing journey of discovery. As scientists continue to study and unravel the mysteries of space, we must maintain our sense of curiosity and embrace the unknown, for the universe has much more to reveal. Voyager 1's mission is a testament to human ingenuity and curiosity. Launched on September 5, 1977, it was initially intended to study the outer planets of our solar system. Its mission was to explore Jupiter and Saturn, their moons, and the rings around Saturn. The spacecraft provided groundbreaking insights and stunning images, including detailed photographs of Jupiter's Great Red Spot and the intricate structure of Saturn's rings. Voyager 1's close flybys of these planets revealed new moons and delivered unprecedented data about their atmospheres and magnetic fields. As Voyager 1 ventured further into space, it continued to send back invaluable data. One of its significant achievements was the discovery of active volcanism on Jupiter's moon Io, which was a major surprise to scientists. This finding changed our understanding of geological activity beyond Earth. The spacecraft also captured detailed images of the complex and varied surfaces of Saturn's moons, including Titan, which has a thick atmosphere that intrigued scientists and paved the way for future missions like Cassini-Huygens. Voyager 1's journey beyond the outer planets took it into the Alio sheath, the outermost layer of the heliosphere, where the solar wind slows down and becomes turbulent. In 2012, it crossed the heliopause, entering interstellar space. This milestone marked the first time a human-made object had left the protective bubble of the heliosphere and ventured into the space between stars. The data Voyager 1 sends back from this region helped scientists understand the nature of the interstellar medium and the boundary conditions of our solar system. Voyager 1's continued operation is a marvel of engineering and careful mission planning. The spacecraft is powered by radioisotope thermoelectric generators, RTGs, which convert the heat released by the decay of plutonium-238 into electricity. This power source has allowed Voyager 1 to operate far from the Sun, where solar panels would be ineffective. However, the power output of the RTGs decreases over time, necessitating careful management of the spacecraft systems to conserve energy. One of the most iconic aspects of Voyager 1 is the golden record it carries. This record is a time capsule intended to communicate the story of our world to extraterrestrials. It contains a variety of sounds and images selected to portray the diversity of life and culture on Earth. The golden record includes greetings in 55 languages, music from different cultures and eras, natural sounds like thunder and bird song, and images of people, animals, and landscapes. This message in a bottle symbolizes humanity's desire to reach out and connect with the cosmos.